All right, here we are for AP Physics. Going to do the last few problems on the circular motion section, the section labeled Challenging Circular Motion Problems. We're going to start with problem 11 here. This is an old AP exam problem. You recognize this is like the rotor ride problem that you looked at last year in honors. We have an amusement park ride with a rotating vertical cylinder with rough canvas walls. Floor is initially halfway up the cylinder wall like this. And then once the rider comes in, stands against the wall, cylinder rotates fast enough, the floor drops, right? But the rider does not slide down the wall. The rider has a mass 50 kilograms, radius r of the cylinder is 5 meters. Angular velocity when it gets up to speed is 2 radians per second. And the coefficient of static friction between the rider and the wall is 0.6. On the diagram below, we want to draw, identify the forces on the rider when the system is rotating and the floor is dropped down. So while he's stuck to the wall, it's spinning around. What does the force diagram look like for the rider? I'm going to go ahead and do this on separate paper. All right. So let's see. Here's what this looks like. I'm going to do my force diagram here. And we'll say, okay. Got my rider, all right, looks like this, all right, hey, all right, everybody likes drawing pictures, right? That's why you take physics, right? So you get to draw cool pictures all the time. Okay, this person on the wall, we say, okay, so forces. So we'll just run through our usual questions we always ask when we're doing force diagrams. What range forces are acting? You'll say, well, it's a gravitational force. Going downward. We'll do contact forces. You say, well, what's touching him? Just the wall. Are they being pressed together? And the answer is yes, they are in fact being pressed together. If I drew a separate diagram, ooh, they didn't ask for this one, but if I drew another diagram and said, hey, look, here's that ride rotating around, say, and here's that person, right, up against the wall, right? You'd say, well, if we're rotating, say, clockwise, for example, then at this moment, this rider's velocity is right, tangent to their path that they're following, right, on the inside here. And so you say, why can't this person continue going straight? Well, the wall is in the way. They're in fact going to run into the wall, right? They're up to speed. They want to keep going this way if the wall's there. If they run into the wall will push back on them with the normal force, which normal forces always go perpendicular to the surface. So it's going to go on the diagram that they want from this view, normal to the wall, right? And then you say the next question we ask, now that we have a normal force, there's a chance, if surfaces are pressed together, there's a chance there could be a friction force. So we ask, is this object trying to slide against that surface? And he is. Gravity's trying to pull him down, so friction opposes the slide. A frictional force is going to go upwards on the rider. All right, and that frictional force will balance out the gravitational. And that's it. There's no ropes or strings or wires, nothing else touching the person, so we are done. That's our force diagram. You'll notice that we're not accelerating up and down the wall, right? We're not sliding. So these two forces are going to have to balance out. But there's nothing to balance this normal force out. That's good. We want that because we know to make this person's velocity turn, we have to apply an outside force to make them turn. That's this normal force, that force towards the center. Centripetal force is going to make that velocity change direction, help them go around the circle. So all makes sense. Okay, part B. Part B says, calculate the centripetal force on the rider when the rider is rotating and state what provides that force. We, of course, know that that force is being provided by the normal force from the wall. Okay, so here's what we're going to do. We want to find the centripetal force. That's a force along the radial axis. Okay, our coordinate axis system that we're going to use for this problem. We're, of course, going to set our axes. We'll have a tangential axis, right, and a radial axis. You know what I'm saying? And then, so this is radial, right? And this is tangential. On this diagram, we've got, this is the vertical, the z-axis. And then this is the radial. Okay, whoops, a little sloppy there. This is the radial axis, okay? Notice that in both these sketches that we drew, you can see the radial axis in both pictures. This is looking down the z, and this is looking along the tangential directions on those axes. You say because we always want to see radial because we know that we're always going to want to analyze the radial axis in any circular motion problem. So that's what we're going to do right now. We're going to take a look at the sum of the forces in the radial axis. Okay, it's got to be, they're not going to balance out the radial. We need an acceleration toward the center. So we're going to get this centripetal acceleration in the radial direction, right? A rad. It's centripetal, of course. So I can substitute in the equation v squared over r for the centripetal acceleration. That's easy. And you say in the radial, we only have one force, the normal force in this problem. And you say, well, towards the center, inward is positive. So this will be a positive force. There we go. So N. And say, now our goal is to solve for this, all right, for this force. You say, well, do I know the mass of the rider? Yeah, they told me the rider's 50 kilograms. Do I know the radius of the circle they're traveling? You said, yeah. They told us it's a 5-meter radius cylinder. Do we know how fast they're traveling? Well, in this problem, they told us that speed there is 2 radians per second. All right, now, it turns out this, when you talk about how quickly you're changing angle, it's actually not velocity. It's technically something called angular velocity that we symbolize like this, with a lowercase Greek letter omega. All right. Now we can change omega into v using the formula v equals r omega. My apologies. I neglected to mention this. I should have just probably told you what the velocity was straight up in this problem. This is the way this problem was originally stated in on the AP exam. But anyway, so the point is my actual velocity in meters per second, I'm going to have to do a little conversion here and say, oh, we've got a radius of 5 meters and omega is 2. And so we're really traveling at 10 meters per second. That's our tangential velocity there. Okay, so the point is I know M, I know V, I know R. I can substitute in, I can find my value for my normal force. And that is the force in the centripetal direction, that force, centripetal force that's making the rider go around. So I take the mass, 50 kilograms times that 10 squared over that radius of 5. In the olden days, like where this problem comes from, you weren't allowed to have a calculator on the exam at all. And so this problem, like the numbers are such that you can just do them in your head, right? You say, hey, 50 divided by 5 would be 10. 10 times 10 squared. Hey, look, that's going to be 1,000 newtons. And that's that normal force. Okay? And so, ta-da. Okay, that is the force in the centripetal direction. What they'll oftentimes do is in problems, by the way, if they ask for the centripetal force, what they mean is the total of the force in the radial axis, which must be centripetal. So if there were multiple forces here, like some going out, some going in, it's the total in that axis that's inward. That's what they mean when they ask about the centripetal force. Okay, just a side note. In this case, there's just one, so it's the same thing. All right. Next, they say in part C, they would like you to calculate the upward force that keeps the rider from falling when the floor is dropped out and state what provides it. We know that upward force, it's this friction force. Now, is the rider sliding? No, we're not sliding around. We're not sliding at all. We're not slipping. So this is static friction. So that is that force is the static friction with the wall. You say, well, if we're not sliding around, these two forces are going to need to balance, right? So if I go to do the sum of the forces in the z-axis now is mass times acceleration in the z. We are not accelerating in the z-axis. So I can, so that drops out. So that right side is just going to be 0. And my force in the z, I'm going to do forces up minus forces down. So that'll be friction, that's static friction minus mg, right? So how big is that static, that force upward? Same as mg. And that's going to be the mass, 50 times 9.8. Now, like I said, in the old days, they didn't give you a calculator. And so then they gave you a break. They said, you know what, we'll just let you round g off to 10 on these problems. The fact is that on the AP exam to this day, they still pretty much let you round g off to 10. Now, personally, I'm always going to use 9.8 because, you know, that's the way I am. And recognize this is 490 newtons. It's not that hard to do 9.8 instead of 10. If I were teaching you just how to score well on the exam, and instead of teaching you physics, then I would probably tell you to round that to 10 all the time. But, man, just rubs me the wrong way. So 490 newtons is that static friction force. Alrighty, and there's one more part. Now they say, hey, at that speed, would a rider who is twice the mass fall down the wall? Okay, if I put a rider that had different mass, would they slide down the wall then? Like mg would be bigger, right? So are they going to slide then? Well, turns out, no. All right. What they need you to recognize here is that mass factored into the normal force and mass factored in here. But you say, wait a minute, do you remember that the friction force depends on how big the normal force? The normal force here is going to get changed by the mass. So I'll have a function of m here and a function of m here. If I go ahead and take this guy, I'm just going to copy it over. But where it says static friction, I substitute in the formula mu n, right? And I know that I actually can only substitute mu n when I'm at the maximum, but that's what we're interested in. If he's going to slip down the wall, that static friction will have been at its max just before he slips, right? So I'm going to solve to see if this friction force can hold him up. It's got to be at least the maximum value, or this force has got to be, at most it can be the maximum value. So mu n, and then how big is n? Well, n is mv squared over r. And so we will see that that mass drops right out. So that mass does not affect how fast we have to make this thing rotate. I'm going to have the same v and the same r, so I'm going to have the same rotational speed, right? Okay, mu isn't changing, g isn't changing, so everything's going to be fine. The mass does not affect how fast this has to spin for him to stay on the wall. So that's it. So we'd say, no. Mass does not affect the size of essentially, if I had twice the mass, I would have twice the normal force, so I would have twice the friction force holding me up. It perfectly balances out is the idea. So I don't know, this is not a good way of wording this. What I want to say is that if I double the mass, I will also get double the upward force because of the way that doubles the normal force, is what I want to say. Okay, that normal force doubles, the friction force doubles, that's holding you up, and so it all balances out. So at that speed, so what I want to say is that changing the mass, actually, specifically, we're talking about doubling. So why don't I do this? If I could say that doubling the mass, oh gosh, it's so sloppy. Let's just say doubling the mass would also double the size of the static friction holding him up. Good enough. And so the mass drops out of the calculation. All righty. Hey, that is problem 11, this old AP problem. Okay.